Hello everyone, we have been discussing the volume change of unsaturated soils. Let me summarize the basic difference between montmorillonite rich clays such as bentonites and kaolinate rich minerals such as kaolin. Even though both are clays, most of the particles are less than 2 micron size, but the behavior is completely different. Under the application of load, when the soils are wet or when the soils are saturated, one soil exhibits swelling, another soil exhibits collapse. So, the swelling behavior of bentonite is due to the montmorillonite mineral in the soil, and collapse behavior is due to kaolinite mineral in the kaolin clay. So, these two phenomena are physicochemical. The volume changes in these two clays is due to physicochemical in nature. Let us quickly go through what difference it makes between montmorillonite and kaolinite. This picture is the basic structure of montmorillonite. Bentonite clays contain high percentage of montmorillonite mineral. So, you have silica and alumina. So, these are this is 2:1 mineral because two silica sheets are attached to one alumina sheet. The alumina sheet is sandwiched between two silica sheets, and this is one basic unit, and such basic units are attached together with weak bonds. You have here water molecules and some exchangeable cations also might be there in the interlayer. So, such different basic units or sheets together is called montmorillonite. The montmorillonite consists of such basic sheets attached in this manner. So, when the soil is wetted or when the soil is saturated, the water can enter into the interlayer space. So, the layers can expand. So, the expansion can take place in between these two. This distance can increase so that layers can expand. And also the hydration of individual cations, exchangeable cations, that takes place, and hydration of interlayers and hydration of external surface takes place, and after that diffuse double layers would form. This causes expansion of the mineral. So, here this is a basic unit of silica. Silica consists of silicon Si4 plus and surrounded by 4 oxygen atoms, O2 minus, and this is attached to an alumina sheet. So, this is gibbsite or alumina Al3 plus, which is surrounded by 6 OH minus ions. So, this is in 3-dimensional view, and a combination of one silica and alumina sheet plus another silica in case of montmorillonite. In case of kaolinite, only one silica and alumina are attached. This is, that is why this is called 1:1 mineral, and montmorillonite is called 2:1 mineral. So, this 1:1 mineral, this whole thing is together is called one sheet. So, one sheet is attached to another sheet by strong bonds like hydrogen bonds. Water cannot enter between these individual sheets. So, because the bond is very strong, so therefore, expansion due to wetting does not take place in kaolin or kaolinite mineral. So, in case of montmorillonite, so the clay particles are negatively charged because you have silica on both sides, and the specific surface area is very high. So, the montmorillonite generally has a specific surface area of 800 meter square per gram, but depending on the percentage of montmorillonite that is contained in given clay, the specific surface area varies. So, the cation exchange capacity is also significantly high. This could be as high as 100 to 110 milliequivalent per 100 gram. Such a high values of surface properties montmorillonite will have. So, generally the bentonite clays will have very high values of cation exchange capacity and specific surface area. So, therefore, the surface potential is very high. So, the potential distribution happens around the clay platelet when this is completely saturated. So, this is the diffuse double layer or film, water film that is formed around individual clay platelet. So, this is a electrostatic potential distribution phi of x, or in a non-dimensional form it can be written as y of x. So, there are several theories whether the electrostatic potential distribution happens in this manner, or there is a linear variation up to certain distance and after that it distributes, it has a Boltzmann distribution depending on different theories. One theory, Gouy-Chapman theory, assumes that there is a Boltzmann distribution around individual clay particles, and this is how the distribution is. And in Stern theory, there is a Stern layer of thickness equivalent to hydrated exchangeable cationic size, and beyond that the distribution is similar to the Gouy-Chapman theory. So, when the clay particle is saturated along with the clay platelet, there is a film that is surrounded by this clay platelet. So, therefore, when two individual clay platelets approach each other, there is a repulsion between the positive diffuse double layer and another positive diffuse double layer from the other particle. So, due to this repulsion, the particles go away from each other, and under gravity the particles will be arranged just one on each other, and the interaction is close to 0. But however, when there is a force or external pressure is applied on individual particles, so the particles approach each other, potential at the mid plane, at the mid distance will start increasing. So, these dotted lines are electrostatic potential of individual clay platelets, but due to the interaction, this is a potential distribution that develops. So, this potential is a phi d, or in non-dimensional form this is u, a non-dimensional mid-plane potential. This is related to the osmotic pressure that is generated due to the interaction of these two diffuse double layers. So, the osmotic pressure that is developed within the clay platelets is related to the external mechanical force or pressure that is exerted. So, at equilibrium, the pressure, mechanical pressure that is exerted is related to the osmotic pressure that is generated due to the given mid-plane potential. If the mid-plane potential goes to 0 or approaches to 0, then the osmotic pressure is 0, then this is under 0 external load condition. So, that is free state. And in case of Stern theory, we have a linear variation of potential up to the delta distance, and beyond that you have the Boltzmann distribution, and this is how the mid-plane potential varies. So, now knowing this, we can easily understand that if you place a soil, bentonite soil, in a beaker, volumetric flask which has water, soil swells and it occupies huge volume. This volume is the sediment volume is significantly high, and this can be compared with the sediment volume that is occupied by the clay in the presence of kerosene. So, this sediment volume is significantly high. This explains that the soil can swell enormously. So, because it can swell under confined environment, it exerts swell pressure on the surroundings which can be measured. If the volume change is not restricted, then it exhibits swell potential, and how the swell potential varies with time we have seen earlier, and the swelling pressure can be obtained by different techniques. One technique is swell and consolidation. Initially the sample is taken, and this is void ratio versus pressure plot. So, initially the sample is taken in odometer cell, and when this is saturated, it swells or the void ratio increases, and this is the at equilibrium void ratio under some seating pressure, say 6.25 kilopascal or 5 kilopascal. Then this is consolidated by applying loading, and this consolidates in this manner. When we draw a horizontal line, and the corresponding swell pressure can be obtained. Similarly, method of equilibrium void ratios can be used where the initial soil sample is compressed in this manner under different loadings, and this is saturated at different pressures, at different mechanical loading, then it exhibits swelling nearly below swelling pressure value, and when the mechanical load is more than the swelling pressure, it starts collapsing or volume decreases. So, when you join this straight line, combining all these equilibrium void ratios after at fully saturated state, wherever this line crosses the initial horizontal line extended from the initial void ratio, that corresponding pressure is swelling pressure. So, the last one we have seen constant volume technique. Here soil is wetted or saturated, and it starts increasing its volume, then you apply small load, then it decreases its volume, and this is how a constant volume is maintained, and it starts decreasing its volume below the initial void ratio if the applied pressure is more than swelling pressure. So, in these techniques we can measure the swell pressure. So, in case of kaolinite, this is a picture from scanning electron microscope. Scanning electron microscope provides the particle associations. So, in this manner, this size is around 200 nanometers. So, the scale is 200 nanometers. So, this much distance is 200 nanometers, and here you can clearly see that the particles are arranged in card house manner. So, huge void space is available in between. This is macropore volume. Similarly, here different particles are arranged in this particular manner, and this is the void space. This is the void space and this is the void space. So, these are macropore volume, and here you have one aggregate. So, this is not a single particle, it is an aggregate of different platelets. So, here in between these platelets, whatever the volume, pore volume that is exists, that is micropore volume. So, this clay exhibits double porosity. So, under applied load, the card house structure cannot be broken, and it maintains the card house structure, but macropore volume slightly decreases. So, when this is saturated, the macropore volume collapses, and particles would get arranged into face to face manner, which reduces the volume essentially. So, it again depends on the pH of the environment as explained earlier. So, when kaolinite is taken in and placed in volumetric flask of volume 100 ml at one particular pH is around 3. So, the volume of the sediment is this much. So, the volume of sediment decreases with increase in the pH in this manner. This is 6.05 or something, and this is 4.97, like that it decreases, and once it crosses 6.05, the soil exhibits a dispersive nature. Here you have a clear solution. Here even though you wait for several months, the soil will not settle. So, this is a dispersed sediment, and this is a clear sediment which is flocculated. These are all clear, and this is at a higher pH, say 7.17 or something, where you have a more dispersed sediment available, and this is a higher pH 7.36 or something, and here you have more dispersed solution, and as the pH is increasing, more and more dispersed solution is available, soil becomes dispersed. So, at a lower pH, lower than isoelectric point of the edge, the particles are arranged in edge to face or shifted face to face manner. So, they settle immediately, and then they form sediments, clear sediments like this, and beyond IEP edge, the particle arrangement is face to face, and they form dispersed sediment in this particular manner. So, the particle arrangements would change depending on the pH environment, also the pore fluid concentrations or the presence of salts in the pore solution, and based on that the particles get arranged into different manner, like face to face or shifted face to face, edge to face, or different arrangements they undergo, and which causes change in the volumes. So, similarly, the low soil, it exhibits collapse due to the mechanical behavior. There may be some bonds like van der Waals forces, etc. They exist between individual quartz particles, silica sized quartz particles, and clay bridges exist between individual platelets because of the negative pore water pressure. As soon as this negative pore water pressure is absent due to wetting, the entire structure collapses. So, that is in low soil. So, as the behavior of individual soil varies depending on either physicochemical characteristics of individual clay or due to presence of suction or presence of some clay content, etc. So, developing generalized constitutive surfaces or generalized constitutive models, still people are working on developing generalized constitutive surfaces relating suction, degree of saturation, mean stress, that is applied load, and volume change, specific volume. So, this will be generalized surfaces can be developed by controlling suction and observing what is the degree of saturation, under what load this is done, and what is the volume change. Such constitutive surfaces are built by conducting control tests. Thank you.